Using the periodic table, specifically utilizing the patterns of the group structure. Use the group structure of the periodic table to predict the empirical formulas for the binary compounds that hydrogen forms with the elements antimony, bromine, tin, selenium, germanium, fluorine, tellurium, and bismuth. So this is a fairly simple problem when you know how the charges and valence electrons determine what exactly the elements in different groups want to form in terms of compounds. So hydrogen here, we recognize this as a 1+ element. So starting with antimony, we find that antimony here is in the group that is normally looked upon with the charge 3-. So we have Sb and H. Sb 3-, H is 1+. To balance out the charges, we switch the charges and use them as subscripts. So SbH3. So antimony. Now bromine, Br. So with bromine, we recognize this column as 1-. So H1+, Br 1-, simply HBr. With tin, Sn, it's in the column that can be, it's looked upon as 4 plus or minus. They can act as positive, or negative. However, in terms of this problem, it tends, while not the best approach, we can look at it as a -4 because of the hydrogen taking on the +1. So Sn 4-, H 1+. So we get SnH4. Selenium, Se, in between 3- and 1- is 2-. So we get SeH2. Germanium, Ge. So with Ge, we're also in the 4 plus or minus column. So GeH4. Fluorine, F, 1-. So HF. Tellurium, 2-. TeH2. And bismuth, 3-. BiH2. Notice how the 3+ and 2+, and obviously 1+, are not included in this problem. It's simply because hydrogen is a 1+. So that means it wants 1 electron. It wants 1 electron to fill its outer level valence. Because 1 plus, let's say +1 electron, we have a neutral a neutral, no longer 1 plus hydrogen, and its outer level valence is completely full. So when we have like H plus F, F has one extra. It has one extra negative, so it's 1 minus. Hydrogen needs one more. So when they form HF, the hydrogen partially accepts the electron that fluorine has as extraneous. And when we have something like hydrogen bonding with selenium, where it's H1 plus and Se2 minus, the Se has 2 extra electrons, and the H only has 1, only needs 1, so it can't take both of the extras from selenium. So that's why it becomes SeH2, because we need 2 hydrogens to accept the 2 extra electrons of selenium. And this concept continues through covalent bonding principles, ionic bonding principles, electronegativity. But this is simply an overview of how the group structure and what we can recognize by the assumed charges of the different groups. So we know, for example, that the noble gases are very stable because they have full valences. So it's very difficult. They're looked upon as inert because they don't like to react with other elements, because their outer level valence is full. They don't need electrons. They don't want to give away electrons. They are essentially non-reactive. However, all these other elements, we're not looking here, but we can see exactly from the periodic table what they want or need to become more stable. Fluorine, chlorine, bromine, very, very reactive, this column, because they want they have this one extra electron they do not want. And I'm speaking about these, I'm personifying these elements, but it's the most clear way to visualize this. They have an extra electron. They don't want it. So they're very reactive and willing to give this up. Same with the group 1 elements. Hydrogen, lithium, sodium, very reactive because they want electrons. Or actually, they want 1 electron because they're only 1 plus. So they only need 1 to become neutral,